Good afternoon, respected professors and fellow researchers. Today, I will present my research on image dehazing technology, which focuses on its development from traditional physical models to the latest deep learning-based approaches. This research is of great significance for improving the performance of computer vision systems in real-world complex environments. The title of my presentation is Research on Image Dehazing Technology, from Physical Models to Deep Learning, and I'm Gaoying Zhao, the presenter of this report. My presentation will be divided into 6 main parts. First, the introduction of image dehazing technology. Second, traditional dehazing methods based on physical models. Third, dehazing approaches driven by deep learning. Fourth, multimodal fusion and related optimization strategies. Fifth, the critical challenges faced by current dehazing technology and emerging solutions. And finally, the future research directions and concluding remarks of this field. Now, let's start with the first part. Part 1, Introduction. Haze is a common atmospheric phenomenon in outdoor scenes, but it brings serious negative impacts on visual imaging, which is the core reason why we study image dehazing technology. Next, I will elaborate on the specific impacts of haze from 4 aspects. First of all, haze causes severe visual degradation of outdoor images. It leads to blurriness, low contrast, color deviation, and obvious detail loss, which seriously impairs both human visual perception and machine vision recognition in outdoor environments. Second, it has a huge impact on safety, especially in the field of autonomous driving. Hazy conditions will hinder the onboard vision system from detecting obstacles accurately, thus increasing the risk of traffic accidents significantly. Third, there are notable downstream effects on computer vision tasks. Degraded hazy images reduce the accuracy of traffic surveillance and remote sensing image recognition sharply, and the recognition performance even drops by more than 30% under heavy haze conditions. Finally, the urgent restoration need. Effective image dehazing technology is critical to restore the fidelity of scene images, and it is the key to ensuring the reliable operation of all vision-based intelligent systems in real-world complex conditions. To better solve the dehazing problem, we must first understand its physical essence. So next, let's look at the physical mechanism of image degradation caused by haze. Atmospheric scattering is the primary physical cause of image degradation in hazy weather. Let's analyze it from 3 key points. First, the physical degradation mechanism. Suspended particles in haze scatter light rays randomly, which changes the light intensity distribution received by the image sensor, and finally results in blurred images and reduced contrast. Second, the key recovery parameters for dehazing. The accurate estimation of transmittance and atmospheric light is the core of image dehazing technology, and their estimation accuracy directly affects the authenticity of the restored image and the preservation of fine details. Third, the fundamentals of modeling theory. The atmospheric scattering model provides a solid physical basis for image dehazing, which establishes a clear mathematical relationship between degraded hazy images and real clear scene images, and lays the theoretical foundation for the design of all subsequent dehazing algorithms. After understanding the basic background and physical mechanism of image dehazing, let's move to the second part of the presentation: traditional physical model-based dehazing methods. Part 2, Traditional Physical Model-Based Methods. The atmospheric scattering model is the cornerstone of all traditional dehazing methods, and it provides a physically interpretable foundation for both the formation and removal of haze, with its core expressed through 2 key parameters: transmittance and global atmospheric light. Next, I will elaborate on the core content of this model from 4 aspects. First, the physical imaging model. Based on the theory of atmospheric scattering, a degraded hazy image is a linear combination of the clear seen image, transmittance, and global atmospheric light. This model clearly reveals the underlying optical mechanism of haze formation, turning the dehazing problem into a solvable physical inverse problem. Second, the function of transmittance. Transmittance characterizes the degree of light attenuation during its propagation through the hazy atmosphere, and it is a key intermediate variable for restoring the contrast and fine details of the original scene. Its accurate estimation is essential for high-quality dehazing. Third, atmospheric light estimation. Global atmospheric light reflects the ambient illumination intensity of the hazy environment, and its precise estimation directly affects the color restoration effect and brightness balance of the dehazed image, which is another core link of traditional dehazing methods. Fourth, the biggest advantage of traditional physical model-based methods is their high interpretability. The model has clear physical significance, and all parameters can be adjusted intuitively according to actual hazy scenes, which provides a clear theoretical basis and optimization direction for the design of dehazing algorithms. Although traditional physical methods have clear interpretability, they have limitations in dealing with complex hazy scenes. With the rapid development of deep learning-based dehazing approaches have gradually become the mainstream of research and achieved breakthrough performance. Now, let's enter the third part. Deep learning-based dehazing approaches. Part 3. Deep learning-based dehazing approaches. In this part, I will focus on two representative and high-performance research directions in this field: polarization-encoded networks and dual-branch feature decoupling frameworks. First, let's talk about polarization-encoded networks. Polarization-encoded networks are a kind of physical-informed deep learning models, which exploit the unique properties of light polarization to separate the direct and scattered light components in hazy images, and even achieve excellent unsupervised dehazing performance in low visibility conditions. Its core advantages are reflected in three key aspects. First, physical mechanism separation. By utilizing the characteristics of polarized light, the model can accurately distinguish the target reflected light, direct light, from atmospheric scattered light, and realize effective component decoupling through modeling based on the Stokes vector. Second, unsupervised depth estimation. The model optimizes backscattering parameters by using maximum, minimum intensity subimages and guided filtering technology, which enables training without paired hazy and clear image data. This solves the pain point of high cost in collecting and labeling dehazing datasets. Third, low visibility robustness. This method performs extremely stably in scenes with visibility below 500 meters, and its edge detection accuracy is improved by 42% compared with traditional RGB-based dehazing methods, which is a huge improvement in practical application scenarios. Next, let's look at another important deep learning dehazing framework, the dual-branch feature decoupling framework, which is designed to solve the problem of mutual interference between content restoration and parameter estimation in single-branch models. The dual-branch feature decoupling frameworks innovatively disentangle content restoration and haze parameter estimation into two independent branches, which effectively enhances the structural fidelity of restored images and the generalization ability of the model. Its core design highlights are 3 points. First, model architecture design. The dual-branch structure fundamentally separates content restoration and haze parameter estimation, which improves the model's decoupling ability and detail preservation performance, and avoids the mutual interference between two different tasks in a single branch. Second, physical constraint fusion. The network estimates transmittance and atmospheric light through multi-scale feature units and introduces physical priors from the atmospheric scattering model into the network training process. This integration of physical knowledge greatly enhances the model's generalization ability on unseen hazy scenes. Third, dynamic fusion mechanism. A dedicated gating module is designed in the network, which can adaptively adjust the weight of the two branches according to the actual haze concentration of the input image. This dynamic adjustment mechanism optimizes the dehazing performance for different haze scenarios, from light haze to heavy haze. The above are the core deep learning dehazing models, but the ultimate goal of dehazing research is practical deployment. So how to optimize the model for real-time and edge deployment? Let's move to the fourth part, multimodal fusion and optimization strategies. Part 4. Multimodal fusion and optimization strategies. The core goal of this part is to reduce the computational overhead of dehazing models and improve inference speed through targeted optimization, thus facilitating the deployment of models in real-time multimodal systems and edge devices. Our research focuses on 3 key optimization modules, and let's look at them one by one. First, lightweight network design. We adopt a streamlined structure based on 2 classic deep learning networks, DenseNet 121 and VGG19. On the premise of retaining the core feature extraction capability of the original networks, we prune redundant layers and parameters, which significantly reduces the total number of model parameters, accelerates the inference speed, and makes the model well adapt to resource-constrained edge device deployment scenarios, such as onboard embedded systems and portable surveillance devices. Second, efficient feature extraction. Aiming at the polarization-based multimodal dehazing system, we optimize the calculation process of the polarized Stokes vector, eliminate redundant mathematical operations in the original calculation, and greatly accelerate the pre-processing speed of multimodal data, including polarization data and RGB data. This lays a solid foundation for the real-time inference of the entire dehazing system. Third, fast filtering module. We introduce an adaptive median filter to effectively suppress the polarization noise generated in the polarization data acquisition process and combine it with a guided filter to refine the transmittance map estimated by the network. This combined filtering strategy not only improves the quality of the intermediate transmittance map, but also significantly shortens the overall processing latency of the dehazing algorithm, realizing a perfect balance between dehazing effect and processing speed. Through the above optimization strategies, the performance and practicability of dehazing models are greatly improved, but current dehazing technology still faces many critical challenges in dealing with complex real-world scenarios. Now let's enter the fifth part, critical challenges and emerging solutions. Part 5. Critical challenges and emerging solutions. Current dehazing models perform well in general hazy scenes, but they still struggle with extreme weather conditions, such as dense haze, non-uniform haze, or nighttime haze, which often lead to residual artifacts and color distortion in restored images. Next, I will analyze the 4 main challenges and the corresponding demand for solution design. First, extreme haze degradation. Dense and non-uniform haze will seriously disrupt the feature extraction process of deep learning models, leading to severe detail loss and inaccurate transmittance estimation. This is the most common problem of current models in extreme haze scenes. Second, nighttime complexity. Low illumination and artificial lighting in nighttime scenes create complex mixed scattering effects, which make the model difficult to distinguish the real scene features from the interference of artificial light, thus leading to serious color distortion and unrealistic restoration results. Third, residual artifacts. Incomplete haze removal or over-enhancement of images will generate halos and texture inconsistencies in the restored images, and this problem is particularly prominent in depth discontinuous regions, such as the edge of buildings and trees. Fourth, adaptive architecture need. The above challenges all point to a core demand. Current dehazing models lack effective dynamic adjustment mechanisms, so they cannot adapt to varying haze densities and lighting conditions in real time. In order to achieve robust performance in real-world complex scenes, dehazing models must be designed with adaptive architectures that can adjust their parameters and structures according to the actual scene characteristics. After analyzing the critical challenges faced by current dehazing technology, we can clearly identify the future research directions of this field. Now, let's move to the last part of the presentation: future directions and concluding remarks. Part 6. Future directions and concluding remarks. Based on the above analysis of physical mechanisms, model design, optimization strategies, and current challenges, we summarize 4 key future research directions of image dehazing technology, which are also the core directions to solve the current challenges and improve the model performance. The first future direction is the fusion of physical priors. Embedding physical laws such as the atmospheric scattering model into the design of deep learning networks is the key to improving the physical rationality of dehazing results. This physical-informed design can also enhance the model's generalization ability on unseen complex hazy scenes. The second direction is to enhance interpretability. Deep learning models are often called black boxes, which limits their application in high-reliability scenarios such as autonomous driving and aerospace. By introducing transparent modules into the network, we can make the decision-making process of deep networks more clear and interpretable, thus facilitating the application of dehazing models in high-reliability scenarios. The third direction is the construction of a joint optimization framework. We need to build an end-to-end joint training mechanism to integrate data-driven and model-driven methods so as to achieve the complementary advantages of the two methods. Data-driven methods have strong fitting ability, while model-driven methods have clear physical interpretability. The fourth direction is to improve cross-scene adaptability by integrating multi-source information, such as polarization, RGB, depth, and thermal infrared data, and designing dynamic modeling mechanisms. The dehazing model can better adapt to complex weather and diverse environmental conditions and meet the dehazing requirements of various real-world scenes. To sum up, image dehazing technology has developed rapidly from traditional physical model-based methods to deep learning-based approaches, and the integration of physical knowledge and deep learning has become the mainstream development trend of this field. Although current dehazing models have achieved great progress in performance and practicability, they still face many challenges in dealing with extreme and complex real-world scenes. The future research of image dehazing technology will focus on the fusion of physical priors, the enhancement of model interpretability, the construction of joint optimization frameworks, and the improvement of cross-scene adaptability. Only by combining physical domain knowledge with advanced deep learning technology and through targeted optimization and innovative design can we develop more robust, real-time, and interpretable dehazing models and provide strong technical support for the reliable operation of various vision-based intelligent systems in complex real-world environments. That's all for my presentation. Thank you very much for your listening.